Okay children, welcome back to the online tutor. So in this tutorial I'm going to discuss the whole lesson of the work power energy, right? So you don't want to check another video, so this video is enough for complete your work power energy part, right? So actually this is small lesson, right? But in our exam we have some structure question, right? So it can be in the essay question as well, but nowadays in the our A-level paper this question is in the structure paper, structure essay, right? So let's move to the theory parts, right? The first you have to understand what is work, what is power, what is energy separately, right? Okay. What is actually work? Work is defined as a product of the constant force and the distance through which the point is application moves under the action of a force, right? So here the work is generated. So the work is generated with the force value and the distance, right? So actually the force is towards the distance, right? It can't be the distance and the force cannot be two paths, right? So both should be parallel to each other, otherwise your work will not be equal. So if you have a component of forces, right, you have to make the component towards the distance direction, right, and find the actual distance of that path, right? Right, so you have to product these two, right? So the forces cannot be inclined, that's what I told you, the work equal force into distance, right? So that is actually the force, right? The work, the what is the measurement of works, right? So you know the forces, so force mean Newton, no? The distance is meter, and Newton meter mean joule. So the measurement of work is joule, right? I think you all know that. Okay, let's move to the power. What is the power? Power is the rate of which work is being done. It's actually easy. Rate of change of work means the work divided by time, no? Right? The rate of change. Rate of change means it's divided by time. In the derivative lessons, you got dx over dt or something like that, no? That is rate of change of the rate of change of the velocity is acceleration. The rate of change of the distance is velocity, right? So likewise the rate of change of the velocity is acceleration, so on. The work, the rate of change of the work is known as power. So it's easy. The work is f into d, no, and you have to divide by time, then f multiply d over t, so which means it is velocity, f into v, right? D over t means the velocity, no? So actually h equal, so the work mean h, right? So h equal, so now h equal f into v, right? So that's all. Right, so you have to memorize that formula. So the most of the time we need that formula actually, right? So let's move to the power, the power measurement, right? The power measurement is, so you know the work measurement is joule, no? The joule is divided by time, the time. So normally the time standard measurement is seconds, right? The joule divided by seconds is js minus 1, which is watt, right? The watt is the power measurement, right? So normally we have kilowatt, right? In our electricity, powers are normally made for the kilowatt, right? So kilowatt means 1000 watt, right? Okay, but the main one is watt, only watt, right? So what is actually energy? In everyday life we count many forms of energy such as heat, light, electricity, etc. We are familiar with the conversion of one form of energy to the another. So actually in our day-to-day life we are using so many energies, right? So many energies mean we are using the electricity energy, we are using the magnetic energy, right? I think you all are watching these days the spellbinder, right? So spellbinder, they make the electricity using the magnetic field, right? Using the magnetic field, the magnetic energy is converted to the electricity. The electricity is can be converted to the so many forces, light, right, sound, so on, right? So actually the magnetic force is really good energy. So actually the fans and all are working with the magnetic, no, So the rotating because of the magnetic field, right? So magnetic field is very important. So in the magnetic field lesson is completely in your physics, right? So it's actually awesome. So I really like that lesson. And when I was doing the advanced level, so the electricity and the magnetic force, the magnetic and all, these are very I mean, those areas are very familiar for me, and I just really like those lessons, right? Okay, actually the energy is the conversions, right? The energy is not a one part, right? It's convert to the many of the forms. The measurement of power is the measurement of the energy is joule, no? So it's you all know that, right? Okay, so you can see in this diagram the conversion of the energy, the electrical energy it's converted, right? The train moving kinetic energy, that the electrical energy it's moved to the train energy. So the train energy mean the velocity mean kinetic energy, right? So these are actually the electrical trains, right? So but in our case we don't have the electrical trains, no. The next thing is the wood chemical energy is converted to the heat energy. The heat energy, right? So the heat energy can be converted to the another one. So basically the wood is converted to the heat energy, right? Right. In the energy lesson, we have few parts to understand. The first thing is kinetic energy. What is the kinetic energy? Kinetic energy is a capacity of a body to do work by virtue of its motion. It's measurement by the amount of work that the body does in come into rest. Right? So the kinetic energy is half into mv square. This is the formula of kinetic energy. So kinetic energy is basically capacity of the body to do work by virtue of its motion. Virtue of its motion. When the vehicle is moving on a road, so that means the vehicle has a kinetic energy. So likewise. Right. So the next one is potential energy. What is potential energy? The potential energy of a body is an energy which a body possesses because of its position. It's measured by amount of work that the body would do in moving from its actual position to some standard position. So so always we have a potential energy, right? So normally the potential energy is measured related to the the land, right? So the earth, right? So the the earth is the standard position, right? So if you take something up, right, from relative to the uh, earth, right? So that height is make a potential energy. So what is the value of the potential energy mean? mgh. So I think you all know this in your physics, you have done this, right? The potential energy, kinetic, those are very familiar for you. So how to find the potential energy? It's mgh. But you just understand for the upward, so the upward, the always the potential energy made noted as a positive, but the downward it's negative. So likewise you just need to understand the positive and negative sign of the potential energy, right? So actually this is relative measurement, that is why we are using positive and negative. Okay, so the next one is elastic potential energy. So this is not in your physics, I think. These equations are also not familiar for you, so you just need to understand this. What is a potential energy? The elastic potential energy, right? The elastic potential energy is a property of the string and spring or compressed spring. The amount of elastic potential energy is half into lambda into x squared over a, right? So actually it's not x, you can put e, right? You can put e. So lambda, no, it's okay, x squared over a, right? So what is lambda? Modulus of elasticity. A is natural length, x mean extension, right? So that is the value of the potential energy. So always positive, right? So lambda, the modulus of elasticity is depend on the material of that spring or the string, right? So it's depend on the manufacturing things, right? Okay. So this is about the energy, right? So actually, so we did work power energy, right? So we get the brief idea about the work power energy, right? So you just need to understand the measurement, you just need to understand the equations, and especially the potential energy. We have signs: upward is positive, the downward is negative. So this is about the work power energy theoretical, right? So after theory I will describe the few more cases, right? Few more cases. These cases will help you to understand the theory of the work power energy, right? So these examples is really helpful to understand some questions as well. Okay, so let's move to the cases. Case number 1. Okay, children, a part of the theory, right? I'm going to derive my whole lesson into few parts, right? Right. The first of all, I'm introducing the question, right? So this is not a question actually. This is an introduction description, right? A car of mass M is traveling on a level road against a resistance R. To the motion, which is a constant at all speed, if the maximum power of the engine is h kilowatt. Right? Case number 1. If the car has a maximum speed of v on a level road. Right? So we just need to make a connection with the resistance and the engine power and the velocities, right, and all, and how to connect a relation, right? The case number 1. In this case, right, a vehicle is moving, mass is m. If the car has a maximum speed v on a level road, so I assume the vehicle is moving with a constant velocity v, and the engine power is h kilowatt. So h mean F, you know what is F? F mean the engine force, and the resistance is always opposite to the direction. H mean H, but 1000 kilowatt. F into the velocity is v. Then we can subject F, it's 1000 H, and also the car is moving with a constant velocity v. It's moving constant velocity. So when I put in F equal ma to the vehicle, then what will happen? F minus r equal m to 0. Right? M into 0. Then F equal r. So r will be 1000 H over v. This is the relation of the first case, the case number 1. Okay, let's move to the case number 2. If the acceleration of the car is a, ms minus 2, and moves on a level road, then what will happen? The car has a maximum speed, right? So if the acceleration of the car is a and moves on a level road, so I assume some instant the velocity is v. Sometimes, so t equal t, the velocity is v. Right? So I just need to make another relation. Again, h equal fe, 1000 h equal f into v. And I'm going to add f equal ma, f minus r, m into a. Then it can be replaced to here. Then r will be 1000 h. Right. So this is the second relation, the case number 2 relation. Case number 3. If the car has a maximum speed v along a straight line inclined at angle alpha to the horizontal. Alright, so again h equal fe, it's 1000 h equal f into v. F means 1000 h over v. Alright, so I'm going to apply f equal ma to the up. F minus r minus mg sin alpha will be m0. This is the another relation of R and HV G sin alpha. Okay, the case number 5. Sorry, case number 4. If the car has the acceleration of a directly up along a straight road inclined at angle alpha to the horizontal. So assume again some t instant, right? Sometimes t equal t, the velocity is v, the acceleration is a. So again we can make h equal fe 1000 h 1000 h over v, and I'm going to again apply f equal m up. It's f minus r minus mg sin alpha equal ma. H over v. This is the resistance R. When a vehicle moving on a straight road, moving on a straight inclined surface, right, with the acceleration a. Okay, this is case number 4. Okay, case number 5. If the car has a maximum speed of v directly down along a straight road inclined at angle alpha to the horizontal. The engine F, resistance R. The velocity is v. Again h equal fe. 1000 h v. And f equal ma to the down. Plus mg sin alpha ma. But the acceleration is 0 real. No acceleration. F means 1000 H. This is the resistance force, right? So now you can understand, so these 5 cases, the resistance are 5 types. But there's no connection with each resistance, right? So always the resistance is depend on the vehicle velocities, the vehicle acceleration, the vehicle mass, or right? It's actually some term, right? It's depend on so many various values, so many variables, right? Okay, so now we can move to the 6th case. Okay, the 6th case, the vehicle, if the car has an acceleration directly down along a straight road, inclined at angle alpha to the horizontal, the acceleration is a. ms minus 2. F equal ma. Sorry, first of all, I'm going to apply H equal Fe. 1000 H F into E. So at some instant, the velocity is V. What about F equal ma? It's F plus mg sin alpha minus r equal ma. This is the FL. So actually this is the end of the theory, right? So these are all theories, right? So you just need to understand. So here we discuss 6 cases in different ways. Some have acceleration, some have no accelerations, right? So likewise several examples for this case 6 up to say case 6. Now I'm going to discuss an example, right? A car of mass M is traveling on a level road against a resistance R to the motion which is constant at all speed. If the maximum power of the engine is H kilowatt and the car has a maximum speed V ms minus 1 on a level road, find the resistance R in terms of mhv. Find the acceleration of the car in terms of mhv and g, and alpha when it's moving. From number 1, at speed v by 3 directly up, at speed v by 2 directly down along a straight road inclined at angle alpha to the horizontal. Right. So we have to answer these 2 wrong numbers, right? The first they ask, a car of mass M traveling on a level road against a resistance R. The car has H kilowatt power. The car has a maximum speed V. So the maximum speed mean, right? The maximum speed mean the vehicle doesn't exist acceleration. It's moving on a uniform velocity V. So it achieved his maximum velocity. Then how can it be accelerate? It's impossible. Find the resistance R in terms of mhv. Okay, let's find the resistance R. Velocity V, the resistance is R, the engine gives velocity force F according to the H equal Fe. then force will be 1000 H over V. Find the resistance R. Find the acceleration of the car in terms of mhv and alpha when it's moving from number 1 at a speed v by 3. So I'm going to apply F equal ma to the up. The engine gives F, the resistance is R. Right, so here F equal R, no? Then R will be 1000 H over V. When we are applying F equal ma, then F minus R, the mass is mg. Mg sin alpha equal to no mass. Okay, the speed is v by 3, no? Then F equal this is 1000 H over V. Actually the resistance, right, which is 1000 H, because it is constant for the all cases. Sorry, it's accelerating, right? Sorry, it's acceleration. The acceleration is A, ms minus 2. We have to find the A. Assume it's A1. H over VM. This is 2000 H over Vm minus G. This is the acceleration of the first round number. And the second row number, it's directly down. With the velocity v by 2, right? Then again, h equal fe. Two thousand. 1000H. Then after, along the straight road, if the acceleration of the car in case 2 is twice in case number 1, find the sin alpha in terms of mhvg. Then A2 will be 2A1 this is 2G, then 3G sin alpha 4000 H over V 3000 This is the value of sin alpha. In this case, find the maximum speed in the terms of v that can be made by the car when moving directly up and the road. So it's again directly up, right? So but its acceleration is 0. The masses are directly up. F minus R minus mg sin alpha equal m0. No acceleration. F is 1000 h over v max minus R means 1000 h over v. It was taken from the previous cases. So in this whole instant, for the whole complete sum, the resistance is same. mg sin alpha means 1000 h over vmg, so equal to 0. Therefore we can see this is 1000h, 1000h, 2000h. V V max equal V by 2. Right, so this is the maximum velocity of the car when it's moving on a straight road with their maximum velocity. The next example, a train of total mass 300 metric tons moves down a directly straight track on an incline sine inverse 1/98 to the horizontal. At a constant speed with its engine turned off, if the magnitude of the frictional resistance for the upward motion remains at the same constant value as for the downward motion, show that the power needed to pull the train up the same track at a constant speed 54 km per hour is 900 kilowatt. Assume that the engine is working at this power when the train is traveling on a straight horizontal track at a speed 18 km per hour with a resistance of the same magnitude as before. Find the acceleration of the train. Take the acceleration due to the gravity g equal 9.8. So we can't take the 10. Now it's 9.8 for this example. So the first thing we have to consider the downward motion. Right? So actually I'm just considering on a 1, right? So it will be easy for now. Three hundred 300,000 10 Newton. This is G, right? This is G. G Newton. The sine alpha mean 1/98. H equal Fe, you know. H mean (900,000 kilowatt). The F is F. The V mean, in here we don't have H actually. Turn off. Then we don't have H. Right? Therefore, this F will be 0. F equal image down. So this is 310G sine alpha minus R will be 0. Now acceleration into 10, 5, 9.8 and 1/98. This is R, right? Then R will be 498. It's 3,4 Newton. So this R is constant for the whole motion. Now let's consider the upward motion. When the vehicle is going up, the train is going up, So now, so H is actually working. H equal Fe. Right? So we don't know H. F into the velocity. The velocity means 54. Right? Six and 9. Two H over 3. This is the force, right? Actually, the acceleration is 0. This is 0, right? Minus R in 3 into 4. This is sine alpha. 90 minus alpha, no? Sine alpha. 98. 0 and 98 cancel. Equals 0. Alright, so now, so H will be, this is H, no? Six into 10, 4. 9, 10, 4. It's 90 kilowatt. Something wrong. Where I got wrong. Actually over here, right? So over here, it's 30, right? It's 30. Alright, so 30 and then another 10. 910 kilowatt. And the next part, with a resistance of the same magnitude as before, find the acceleration when a train is moving on a track horizontal road, right? So H mean 900 kilowatt. So F will be 1000 over. The velocity mean 18,360. MA. Right, so the F mean 18 and 3 and that's 3 4, right? So 18 and 4 equal the M mean 300 and metric ton A 15 10 4 300 10 3 equal A. Okay children, the next example. A vehicle of mass m kilogram pull a trailer of the same mass by light and accessible cable along a straight level road. The resistance to the motion of the vehicle and the motion of the trailer are R and 2R newtons respectively. Show that the instant when the engine of the vehicle is working at the power P kilowatt and the vehicle is moving with the speed V, the tension in the cable is half times this one. Right, so we just need to find that tension. So I'm going to draw the diagram. Alright. So the diagram will be this is the trailer, right? Tension is T. The resistance is R and R. P kilowatt, H equal FV. Right? The velocity is V. So H mean P1000 F into V, 1000 P over V. So I don't know the acceleration, I assume it's ms minus 2. Now for the A and B, for A F minus R minus D equal M into acceleration is A, equation number 1. And the trailer B T minus 2R then This is the tension of the string, right? So what I did, I use H equal Fe first, and I apply F equal Ma here, and I substitute. I simplified it as simultaneous, and I got the tension. So this is the way of finding the answer of these kind of situations. Okay, the next example, the last example of this tutorial. A lorry of mass m metric tons moves in a constant velocity u along a straight level road, with the engine working at the power h kilowatt. Next, the lorry with the engine working at the power 2h moves up along a straight road inclined to the horizontal at the angle alpha, and the resistance of the motion is the same as the resistance of the horizontal motion. Show that the maximum speed of the lorry in this case is this one. A lorry of mass m is metric tons moves at a constant velocity u along a straight level road. The engine power is h kilowatt. The next lorry with the engine working power 2h kilowatt moves up along the straight road. Okay. So I'm going to draw the diagram. The first lorry. Alright, mass is mg, h kilowatt. H equal Fe, 1000 H equal F into V. The V mean U, no? Mass is m. Sorry, this is 0. H over u. The next lorry with the engine working, right? So here the next lorry with the engine working at the power 2h kilowatt moves up along a straight road inclined to the horizontal at the angle alpha, and the resistance to the motion is the same as the previous. Show that the maximum speed of the lorry in case is this one. So maximum speed means we have to avoid the acceleration again. H equal Fe, 2H equal V. So V max, 2000 H over F. Again this is 0 because the acceleration is 0. Resistance is 1000 H minus mg sin alpha. So you just need to subject Vm. Actually the mass is metric ton, right? So mass mean metric ton. This is metric ton, then this is m into 1000 g sin alpha. All thousands getting cancelled. No g here, no g, right? So now we can subject Vm, right? Two h Vm h over v समान m sin alpha. 2h over Vm m sin alpha h over v mv sin alpha plus h equal this is 1000 u, right? 1000 u hu Okay, this is the value of actually I miss G, right? Here it's mg, no? mug. Vmax. Okay children, so this is about the other work power energy, right? So in the work power energy we don't have the pump cases, right? And actually this is moving on a straight road cases only. The vehicles are moving on a road, right? The straight road and the inclined road, right? So those are in our combined mathematics work power energy. You don't want to study the pump cases and all, right? So actually you can try it, right? So the in the past paper books, very later questions, so the 2000, like 2000, 2001, 2, right? Like these years they ask the pump cases and all, and you can check those things, right? But actually you just need to do some questions, right? So you can do the latest work power energy examples, right? So okay, so thank you very much for being with us, and have a nice day, and I will catch you with another session. So this is the end of the work power energy lesson, right? Okay.